record in this computer. All right. So let's do a quick review and see what we did last week. So what we did last week? We did a lot, correct? So last week we said, the main concept, if you have any digital design or circuit design, the input is more than 6, we should use different approach. If it's less than 6, what we have to do? We can use the K-map. So that's something we can manage, and it's not a challenge. If up to 4 or 5, the size of the table, it's really manageable. But the problem, when it's more than 6, it's going to be tough. So for 1-bit adder, remember when we did the 1-bit adder, if you're trying to add 2 numbers, okay. All right, what is the extreme scenario here? So if you're trying to add 2 numbers, what's the highest value? It's 1 and 1. So if you try to add A and B, what's the result will be? Will be sum and carry. So here it's going to be 0, 1. So always you will have 2 input and you will have 2 input and 2 output. However, if you're trying to use the 4 bits or 2-bit, still there is a carry coming in from the stage before. So that's why for the 1-bit adder, so how many inputs you will have? You will have 2 and you will have C1, correct? That's the carry from the previous stage, from stage 1. And you will have the sum and carry. And that's 1 bit. Now, if you want to extend that to 4-bit, how you do that? If you want to build a 4-bit adder based on the 1-bit adder, how you do that? Good. So simply we put 4 next to each other. And the carry from the first one, it's going to be the input for the stage 2. And the similar thing. And if you remember, when we did the delta, what is the delta in this circuit? Correct, 3 delta. And I will show you based on the equation now when we do a review. So it's 3 delta. Now for the rubber carry adder, what is the total delta? 12. Can you explain that for me? So up to here 3, and then it's going to be 6 delta here, 9, and then finally here is 12. It's 12 or 13. 12, correct. Because the last sum is not depending in the C3. That's going to be the last carry, all right? So far we improved our circuit, correct? So far we didn't improve anything. We just used 12. Now if it's 4-bit, the delta will be 12. So now let's do review for that. So how we did that? So before, how we know it's a 3 delta here? Remember, when we do a 1-bit design, so we say, we'll have A0, B0, correct? Then you will have C minus 1. Then you will have sum 0 and carry, correct? 0. So, and for the K-map, how many tables we need for the K-map? We need 2 for the C0, 2, 1 for C0 and 1 for sum 0, correct? What is the size for each table? 2 to the power 3, because we have 1, 2, 3 input. That's from last week. Still, we did not do anything new yet. So then from there, and that's part of your assignment, right? So, and can I, oh, nice. Can you see it? Yeah. Maybe if we turn the light here. It would be more clear because by hour and a half. Because we have to go. My cousin did a surgery today, one surgery, 6 hours. I'm trying to go to the hospital to visit him. All right. So from the K-map, it's really simple, correct? That's the table, the first table. And that's for the sum. And we'll have A0, I'm sorry, AI and BI. You will have CI minus 1. And just simply, we have to throw the numbers, correct? So I'm not going to go over all of them. If you want to pick up this one, which is this one, correct? So what we're trying to add here, remember, it's going to be 1 and 1, correct? And what is the carry minus 1 is 0, correct? So what's the result? Sum of 0 and carry will be. So that's why we have 0 here, and that's why we have 1 here. Perfect. So if you do that, if you fill out the whole table, that's what you will got, correct? 4 ones here, then you will have 1, 1, 1. And from last week, what we said for this ones, not much we can do. So it has to be separate, correct? Now, because you cannot combine them together. Again, remember the K-map, the purpose of the K-map is try to reduce the circuit. And how we do that? By combining or eliminating the difference. So that's why now we cannot combine anything. So it has to be separate. So it's going to be a big circuit. And here, if you remember, we can do this way and this way and this way. I'm sorry, this way, correct? Hopefully, yeah, that's not part of us. So you can do this way. That's you combine minimum. However, because we have already here, if you remember this one, it's the sum here come as A XOR B XOR C, correct? C minus 1. So is there a way for this to reuse the XOR here? Yes, by what we did here, if you remember? We say we will do just combine this two, then combine 1 and 1. And when you write the equation, all right, the equation will be from here. It's AI, BI, correct? And from here, it's going to be CI minus 1, then and it with AI XOR BI. You know how we got this one? Explain it. Yeah, let's do it for you just in case. So this one is straightforward, this two, correct? Now let's take this one. What is this one? This one is CI minus 1, correct? And is BI. Because, we'll take both of them because, both is different. It's not common. So it's going to be AI bar and BI. Then or with what? We'll try this one now, which is CI minus 1. Okay. Which is A and BI. Well, okay. So then in this case, what we'll do, we'll take the common, these two common. It's going to be CI minus 1. Then we add AI bar BI. Okay. Or AI BI bar. And this one, we call it XOR, which is AI XOR BI. That's why we have it here. Clear? So why we did that again? Why? What's the reason? What's the reason we just only took this one separate? Why? To be able to reuse the XOR. That's the whole idea. In this case, you're saving hardware. You're already building the XOR in this way, so you will have it in your circuit. Just you just reuse it. All right. Now, what's the delta we said? 12. Perfect. And that's the issue. What's the issue here? Why we have the big delta? Because we are waiting on the carry. So the carry is holding us. So if there is a way to break the carry or find all these carries in the same time, you will save a lot of time. So again, that's why we call it carry look ahead, or the method is called look ahead approach. But since that's an adder and we're trying to just find the carry using the look ahead approach, to find the answer quicker. So the technique here we're trying to eliminate the carry. So stage one should not rely on C0. If you can find the C0, quicker, then that will speed up our process. So how we can do that? That's the approach. Simply we need something called look ahead unit. Correct? Carry look ahead unit. And this unit, what's what this unit will provide to us? So it's gonna give us the C0, C1, and C2, and C3 at the same time. So that's a technique. Before here, in this way, C0 has to wait until you have the C0. And C2 you have to wait until you have C1 and C0. So they are depending on each other. But if there is a way to use this unit or this circuit, we'll see how we build that, then it will save the delay. And if you remember, the technique of that, that's not part of the assignment, right? Okay, good. Because if it's part of assignment, it's easy for you to do it. So, okay. And to do that, what we did last time. So what is the trick here? Now, if you're trying to add two numbers, okay, and there is numbers before and there is number after, all right? So we're trying to find terms, what these terms, again, what we are trying to find, what's our focus? On the carry. So that's what we're trying to find. Where is the logic? Where is the condition we can decide we have a carry or no, before long time, before even we got to the stage, the similar or the current stage. So how we can do that? So we have something called generation concept. So when you will have a carry out, when the carry here equal 1, okay, if your input is carry equal in this stage equals 0, what is the condition for that? There is only one condition, correct? When you have 1, 1, then you will have carry. So that's why, if you see the equation here, you will have a carry in this stage. You see this one? In this stage, which is stage I. So you will have a carry in this stage only in one condition, which is the carry when we have A, I, B, I. When A is 1 and B is 1, then the G will be 1, correct? So that's the first condition. Now, what is the second condition? When you will have, let me delete that again. The second condition, when you will have a carry here, so when the carry here equal 1, okay, when you will have the carry equal 1, if your carry input equal 1, what that means? So when, now, if both of 1, let's see, if both of this 1, what we will have? The carry will be 0, so it will be 1, 1, 3. We will have a carry. We will have, but the carry, what's the reason you have a carry? Because you already have the carry from the previous stage. If the previous stage you don't have carry, then you will not have a carry only in one case, when both of them is 1. So in this way, what is the condition? The condition, you will have a carry when in this stage you don't have a carry. However, the carry is propagate from the previous stage, correct? Simply. So in this case, what is the condition will be? You have two conditions. Either one of them is 1. So either A equal 1 and B equals 0, or A equals 0 and B equal 1. So one of them equal 1. If both of 1 or both 0, that will not work, correct? So in this case, what is this equation for the B? It's the A XOR B. Clear? So from here, what we did, which this circuit we called last time is the BG block, correct? You know, let's draw that here. So that is your block. I will name it BG. Okay. Oh, sorry. BG block, correct? And what's your input here? A of I and B of I, correct? What's your output will be? And again, and you will have one. You carry -1, correct? Because that's we need that. And what you will have out here? No, that's going to give you the G and the B, correct? And what is the circuit inside? If you want to clean that and try to draw. Okay, let me, oh, nice. Okay, what is the circuit for the G? Just remind me. And gate, and what you will have A and B. And the other one is the XOR. So this B is going to be the XOR. And it's going to be A and B. Is there a need for C? C -1? C -1 has no effect, correct? All right. Oh, I'm sorry, has effect. Okay, that's for the sum. Okay, I'm sorry. So has no effect. So that's the B and G. So now we need this circuit in our full design. We need, first we have to find, remember, you will find, so if we have 4-bit adder, you will find all the B's and G in the same time. You will have B0, G0, B1, Z1, and we will see the full circuit. But the point here, that's the initial stage. We need the B and G to be able to continue. All right, so now, from previous, what is the equation for the sum? Remember? That's, you can, yeah. You know, now I like the laptop more. Now I can, all right. So what you will have, yes, we will have the sum A XOR B XOR C of I. And if you see this one, what is this one? A XOR B, it's the B of I. That's why we replace it with the B of I. Then XOR C of I. Now, what is the C, the carry? It's A and B, C of I, then A XOR B, which is G of I, correct? Because this one equal G of I. Just we replace it. And the BI, the XOR, it's equal BI. Simple. So let me just delete this stuff and let's focus on, and I think there is a way to change. Yeah, maybe this one. Oh, nice. Okay. So I needed to keep that in your mind, and that's in your mind. All right. So the sum and the carry here. All right. So now let's put some numbers. Now let's find the carry 0. I needed to find, I know it's there, but let's write it together here. Oh, I'm sorry. Where's my eraser? Okay. So now let's find C0. I have it, everything here, but I'm trying not to show it to you. So let's work together. C0. What is the C0 from here? It's G0 or B0 and C -1 is C -1, correct? Perfect. So can you explain that to me? Logic. What we mean by that? You will have, and the first stage, remember we have, if we have 1 0 0 0 1 and 1 0 0 1, let's just say, no, let's do the number. What that means, you will have a carry here, you will have a carry equal 1 when there's 2 conditions here. Either you generate it here, correct? So that's why we generate it at the stage 0, or it's coming from outside, okay, and propagate through the level 0. So if you see that it's coming from outside, if this one equal 1, all right, and propagate to level to level 0, then you will have carry. The carry 0 equal 1. All right. So that's the meaning. Now, we don't have to go all of them, Z0, 1, 2, 3. Now, if I ask a question, if I delete that, I ask a simple question. Can you find C3 for me without even do any equation? Think about it. When you will have carry. Either first, remember, how many levels we have? Okay, what we will have when you will have carry. First condition. What's the first condition? It's from P3. If you generate it here, correct? Because I'm looking. Remember, I'm looking for carry 3, so the carry is coming out here, correct? So when you will have carry 3 equal 1, first condition when you generate it at this level, correct? So you don't care about the previous because you generate at that level. That means you will have it. All right. Second, or what's the or? Before. So you generated first. You generated here. You generated at this level. However, you propagated to level 3. So you propagated to this area, this level. Okay. Now, what is? I'm sorry, G2. This one, correct? Or, can you give me the or? Where you want to generate it? And G1 here. Remember, that's level 0, 1, 2, 3, correct? So you generate at this level, and then what you do? Let's go to propagate to B2 and B3, correct? Then, or what's the condition? You do it here, correct? You generate it as G0, propagate it through 1, 2, and 3. Or what? Coming from outside, correct? Which is mean C minus 1. Then it's go through B0, B1, B2, B3. Correct? Clear? So it's logic. You don't have to now do equation. If you think about it, you will be able to write the equation for C3. Now, if I give you in the exam, if I tell you, please find C7 for me. Can you do that for me? It's the same thing, it's the same thing, but it's gonna be how many? So we have a 3. How many levels do we have? 1, 2, 3, 4, 5. Correct. So when you have C3, it's gonna take 5, or it's gonna take an OR gate, correct, with 5 input, correct? So what is the size of the C7? The gate. It's gonna be 9, correct? All right. And that's why nobody uses, because you will have a delay. We're trying to eliminate the delay, but when your gate has more than 4 input, now you're going to the other direction. You're climbing, and then all of a sudden you start, going down. So that's the problem. Clear? So that is the C3. And simple, we just did that together. We did the G3 we do it together. So you don't have to memorize that. In the exam, I think that will be something simple for you, just to think about it and draw it in your mind how the carry will come from stage to stage, and you will have the answer. All right. And what is now? Let's talk about what the carry. What is the carry here? So remember, now we remove that, correct? We don't need this one. So now the carry is gonna go from here to here. It's gonna go from here to here. It's gonna go from here to here. What is the delay? 4. Why? Yes, but before that, is that the right circuit? No, we change it. Because remember, first what we have to do, I have the full drawing, but let me. So remember, we will have the B and G block. What's the delay for the B and G block? 1 delta. Why? Because you will have A and B, it's only 1 gate, and the BI, it's XOR, it's 1 gate, so it's the same level. So it's not 2 levels, 1 level. That's why we have 1 delta. But in a theory, it's going to be 2 delta because XOR, you know, it's a simple, we think it's a simple circuit. No, it's 2-level circuit. But now we assuming it's 1 delta. So we will have 1 delta. Then this one has to go to the carry look ahead circuit. And this one, again, remember when we expand, we can, even if it's complicated, complex, when we keep expanding the circuit or the equation, we will get to the point we have only how many levels? 2 levels. So that's mean the delta will be 2. Okay, you said 4. Why? 4 is correct.
Yeah, that's 4.
So you have 1 and you will have 2 here. Why it's 4? Yeah. So now we have 3. Where is the 4? No, the carry we got the carry from here. So we got the carry after 3. Correct. So remember, the sum, it's an XOR gate. So after here, you will have the sum as an XOR gate. It's coming and it's going out. That's the another 1 delta. All right. So that's why we have 4 delta. Now, did we improve the delay here? We went down from 12 to 4. That's a huge improvement. And as we mentioned before, is that enough? It's not enough. Okay, so we have to improve that. All right, so, but let's go, before we go that, yeah, remember we mentioned that. So last week we mentioned that when you have a gate, any gate has more than 8, in general 8, okay? Okay, the delay will increase and you will not have a benefit of expanding. So in theory, they stop up to 4. So when you have a gate with 4 or 5, okay, then you will be fine. You know, the delay, you can control the delay, but more than 5, you will have a problem. That's why we stop with how many bit adder? 4 bits. So 4 bits, if you do 4-bit adder, and you will be fine, correct? So now, question for you. If you want to do a design for 8-bit adder, can we use the carry look ahead? All right, can we do that here? Can I do that, for example? Give me 1 second. I don't know where's the, okay. So let me try to draw it here. So if I have 8 of them, correct? 1, 2, 3, 4, 5, 6, 7, 8. And you add them to carry look ahead here. What you will have output here? C0 up to C7. What's the equation for the C7? It will be 9 ORs, correct? That's mean your circuit with the OR, it's gonna look like something like this. You will have 1, 2, 3, 4, 5, 6, 7, 8, 9. And what we said about this design, we're not supposed to use a gate with more than 5 input or 4 input. You know, let's assume 5 because we did 2. So in this case, can we use 8-bit carry look ahead? Can we use that? No, we cannot use, you know. So in this case, what we can do to solve this problem? All right, so what you can do, you will have here, okay, 4-bit adder, correct? And in this side, what you have here, you will have carry look ahead for 4, correct? For 4 bits, correct? And you can use the same one. It's 4-bit adder. And of course, you will have 4-bit, and you will have the carry look ahead. Perfect. So, and here, what you will have here, what you will have output here? C0, C1, C2, and C3, correct? Then, what we have here? C4, C5, and C6, and finally C7, correct? Now, how we can combine these two together? Simply, you would have the carry 3 and make it as input for the next one, correct? So what is the delay in this case? What's the delay to get the C3? 4 delta. 3 delta. 4. C3. After how long we 4? Yes. C3. 3 delta. Because remember, all the C's, C0 up to C3, we will have them at the same time after 3 delta. So we don't have to wait for the sum here. Remember, there is 1 delta for the sum. We don't have to wait for that. I have it there. So you will have C3. Then it's going to go here. How long is it going to take to get C7? Another 3. So you will have 6 delta, correct? But overall, to get the sum, what's the, how many delta you will have? 7, because it's still the last sum here. You will have the sum. You need a delta. So if you use this way, okay, you will have 7 delta. Perfect. Is that good enough? No. Can we prove it? Yes. How? What you can do here to improve your circuit? You cannot remove the C3 because you need it. Yeah, but what's the problem? The problem, yes, the problem, we are waiting on C3 before we start the second circuit, correct? So if there is a way to break this one, if there is a way to break this cable or this link, if there is a way to break that and find all the carries in the same time, then you will save some, or you make the circuit speed higher than 6 to 4. We have 7 here now, correct? But how we can do that? Simple answer is to add another carry look ahead block. Now, this one, what we name it? Carry look ahead, correct? So what we can name this one? Ahead block. So remember, this one, it's 1 bit, correct? And what this one? It's a block, correct? So can we name this one block carry look ahead? So we name it like this, correct? We'll see how. But the point here, now we can add. And what is the size of this one? If you have only 2 blocks. So what you're trying to find here? C3 and C7, correct? All right. Okay, but now let's do 16 bits. Because in this case, we can use the same circuit what we're here, because this one is 4 bit. And can we use the same circuit? We'll show you now. So let's go here. What's the problem? Yes. How many the blocks now? The block carry ahead. Okay, what's the input to that? Because you have to equate. When we do the equation, you will see the maximum gate will have the 5 input. Okay, now we will see it. So it's not going to be a problem. All right, so as we explained before, that's how it's going to look like. The problem, as we said, this link, we're trying to eliminate that, right? So you will have 4, and you will have another 4-bit using the carry look ahead circuit. All right. And just use the carry, waiting for the C3 to finish. Then you pass it to the next block. And the total will be C7. That's the issue. All right. So what is the total delay? 7. Okay. And we say how, correct? I don't have to explain myself again. Is there a question so far? Now that's 8-bit. Now let's make it 16-bit. So if you're doing a design for 16-bit, a carry ahead, okay, using only 4-bit look ahead circuit, how you will do that? How many blocks you need? 4, because you will have 4 bits, 4 bits, 4 bits, 4 bits, correct? Total will be 16 bits. So if you want to draw the circuit, if you want to do a big box here, okay, you will have A from 0 to 15, and you will have, what you will have here? B from 0 to 15, 16-bit, correct? All right. So, and how we combine them together? Just we take the carry from C3, pass it to the next stage, then 7, you pass it to the next stage, then C11, you pass it to the last stage, then C15, the output. What is the total delay here? 3. It's going to take another 3, 6, then another 3, 9, and another 3, 12. 12, then you will and then this one will be, the final will be 13 to find the whole result with the sum, correct? Not just the carry. All right. So again, what is the delay? 13. How? We explain how we did that. Okay. Can we reduce that 13 delta? Yes. And how we do that? Again, just remind me how we can do that by eliminating this connection somehow. And how we can do that? By using the carry look ahead approach. However, this time it will be a bigger one. It will say it block carry look ahead, just the block, not just bit. So how we can do that? How's the circuit? You know, you will use the carry look ahead block, and the purpose here to find C3, C7, C11, and C15. Perfect. So let's repeat ourselves. Okay, from the 1-bit we did what we find the G and the B, okay? And based on these two, we modify the sum and the carry. We did that already at the beginning. Then we find all the C's and 3, C0 up to C3. Now let's think about the new logic now. So now let's rewrite the B and G. And what we will name that? The first one, remember, we name it B and G, correct? Now, since we are using the block, what I will name it, remember, I will name it B block and G block, correct? Are we agree on that? So that's just to know the difference. Now, the question for you, I needed to, try to correct me if I'm wrong. Sorry. Hopefully there's no class here today. Okay, now let's go to the G. When is the G block? What's the equation for the G block? Or G0? Now let's do the B, maybe it's easier. Now, if you want to find the B0, what's the answer? I'm talking the whole block. There is only one condition. When the carry here, you see the C3, okay? When this carry will be 1, when you will input equal 1, then it's propagate from here, then to here, then to here, and then to here, correct? So you have to go through the whole 4 bits. You have to propagate from from the outside word to the end. So what's the result will be? So you're just going through the each level and just pass it, propagate the carry to the output. So now what about the G0? What's the answer? Remember, that's a stage 0. What we will have here? Remember, we'll have B0 and G0, correct? And here you will have B1, G1, G2, B2, G3, and B3. So what is the condition? So either you generated in this bit, okay? So that's why you generated at G3, or you generated here, that's why, and then you pass it through B3. So that's the second condition. What's the third condition? Correct me. Here, this block. What we do here? So either you generate it at 1, and then propagate it through 2 and 3. So B2 and B3. What about here? It's generated here at G0, then it goes through B1, B2, B3, right? Okay, and it's coming from outside. Why we did not include the outside word? Is there a need to include that? There is no need in this case because it's coming from the G's and B's, right? Not from the G block and the B block. Okay, so we've been able to find B0s. I'm sorry, B0 and the GB0. Is there any question so far about how to find the GB0 and that's for the first block. Remember, we have 4, and each one has 4 bits. So in this case, what's our output here? It's the GB0 and BB0. Perfect. That's only for one. Then you will have another one here. And if you wanna do that, what's your output here will be? Yes, because it's a block 1. Remember that we call it block 1. I'm sorry. That's block 0 and that's block 1. So it's gonna be GB1 and BB1. Then you will have the third one and the fourth one. We will see the full circuit, but that's the concept. So what we did here, we just follow the same process, when we did only the 4-bit adder, we find the G's and the B's, correct? And we found the equation for it. And then now when we have a 4-bit, we're trying to find the new G block and the P block, correct? So what that's mean? We need a block circuit, a new block. Remember the first one over there? Remember when we did AI and BI, we find the B and G, correct? All right. Now similar here, but here how many bits you will input? Just 1, because I'm doing only for 1 bit. Here in the block area or the block design, you will have 4 inputs. And what is this 4 input? If you go back in this circuit, what you have there? But which one? Which G and B? Not the block, the original one. It's for the bit. So that's why your input for the block GB is that we name it block B and G's, correct? That's the new block. That's the new circuit we needed. All right. And what's the input for that? It's gonna be the original B's and the original G's, correct? And what's the output? It's gonna be B, GB of I, and the BB of I. So this one, you take 4 input, but here it's gonna be only 2 output. And for example, if you are in the stage 1, or I'm sorry, stage 0, what's the result you will have? GB0 and BB0, correct? What's your input will be? Remind me. It's going to be B0, B1, B2, B3, and G0, G1, G2, G3, correct? Now, when we put the whole circuit together, it will be more clear for you. But we're trying to find how we will achieve the final result. All right. So we'll follow the same steps. You know, we try to find where we generate the carry, because always our problem with the carry, not with the sum. So here now we find the new where we generate the carry when you have a block of 4-bit. You have 4-bit. Now when at the end, not the first bit, not the second, not the third, the last bit where we will have a carry. So again, we said we generate the carry when it's coming from the outside, then and you just propagate it to the stages until you get the result. Or what we said, either you generate in each bit in within the 4 bits. So either in the G3, then it's going to be outside, or you generate it at G2, then you propagate it through the B3, or you generate it at level 2, and then you move it through 3 and level 1, then you move it through 2 and 3. Finally, from level 0, then you move it from 1, 2 to 3. Okay, so it's the same concept, but it's bigger, circuit. All right, so in this case, what's is gonna go inside? It's clear? Yeah, it's clear. What is gonna go inside the 4-bit block CLA unit? Remember, first of all, what's the output? What we are trying to find? C3, because we have a problem with it. C7, C11, and C15. If we can find those 4 earlier, that means we'll be able to reduce the delay. And what's your input to this one? Remember, we said the B's and G's, correct? From the 4-bit. So that's why we need this circuit. Okay, so you will have B0s and G0s. I'm sorry. It will be this block. I'm sorry, this block. That's gonna be BB0 and the GB0. Same thing here. What you need? GB0 and I'm sorry, 1 and 1. Similar here. What you need? 2 and BB2. Finally here, what you need? GB3 and BB3. All right. If you have this input, then you will be able to generate that. Okay. And again, from where we got this 2, how you got them? Because we have a circuit, we build a circuit, correct? This one, the block BG's unit, that will generate the BB0 and GB0, okay, for the first block. The same circuit, we'll use it to generate the BB1 and GB1, correct? The GB1, yes. So we'll create that. So we'll show you when you have the full circuit. All right?
For the block BG unit, it looks like there's 8 inputs, so that's slow down.
Which one? This one?
Yeah.
Well, what's the actual equation?
All right. Yeah.
All right. So, but you're not going to use all of them. So it's only 4 OR gates. We have 1, 2, 3, 4. So still within the recommendation, is not big. All right. All right. So, and now let's find. Remember before what we did when we find the B and G's. Remember when we find B and G, B of I and G of I. What we use that for? To apply it to the carry, because the whole purpose to find the carry. So in the 4-bit design, what we did, we found the C0, C1, C2, and C3, correct? Now here, what we need here, what we're trying to find. We're trying to find C3, C7, and C11 and C15. Now let's compare the equation for C3, the one we did before, and I'm sorry. So with the new design, so when we find, maybe here, make it easier. I'm sorry, here. Let's look here. Logic for the C3, the carry 3, will be similar to logic carry 0 from the 1-bit design. So how we did that? So that's the equation. Remember the C0? What's the C0? Remember what we said when we will have a carry at the stage 0? When you generate that at G0, when you generate it at the stage 0, or it's coming from outside, then you propagate it to level 0. So that's the equation. Now let's compare that to the bigger the block, you know, the block BG units. So that's the equation, correct? So when you will have carry 3, when you will have a carry 3, when you generate that at P0, correct? When you create it, when you generate the carry at the whole block, which is block 0 for now, all right? Because I'm trying to find only C3, which is the first block, not the second, not the third, not the fourth. Okay, the first block. And this block usually will find the GB0 and BB0, correct? So when you will have a carry 3 C3, when you will have it, when you generate it at this block, or it's coming from outside. So what's the equation will be? No, just you propagate it through the whole block. And C minus 1. It's similar, right? But now we're looking at the bigger. You have a class here? I'm not sure if they have a class. If they have a class, they will kick out. Let me off. We have a class of 6 because he has an issue, the same issue. So in the other class. All right. Huh? No, like, oh, okay. I'll tell them I'm here. So let them find a place. So now we've been able to find C3, correct? Now, can you compare C7? Now I'm trying to find the C7. C7, I can compare it to which one of the C's before? C1, correct? Because it's that's, remember the C1 is the second bit now, but the C7 is the block number 2. So block 0, 1, I'm sorry, block 0, block 1. The C1 is bit 0, bit 1. So it's the same location, the same sequence. That's why I compare it to C1. So can you give me the equation for the C1 quick? Mostly they will kick us out, but let me try to finish. At least if I finish the adder, that will be fine. Still, I have the comparator. It's a very interesting topic, but let's see. Now, what's the C0? Just remind me. When you will have carry as C0? Now, I think now it's become easy to remember G1. So you generate it add that G1, or you generate it as level 0, and you propagate it through 1, or it's coming from outside, and it's going through B0, B1. Now, can we rewrite that with the the block B and G? Yes. So how we can do that? So C, now what with this one? We C7. What is the C7? It's either you generated at the block 1 or generated at the block 0, then propagated through block 1. Perfect. Or the last one, it's coming from outside, correct? And get it through 0 and through, sorry, 0. I'm sorry, 1. It's coming from outside. All right. So that's if you read the equation here. So either you generate it at the block 1 or generate at block 0, then propagate it through block 1, or it's coming from outside and it's propagated from block 1 to block 2. All right. Clear? It's become easier, more logic, just you don't have to memorize it. Just think about it. Where I generate my carry, in which stage. When I looked, yeah. This class should be until 9. No, we start at 5 and hopefully we'll finish by 7. So hopefully. I already emailed the help desk about the projector. Are you working with at the help desk? You're working there? And it's okay, that's your problem then. So make sure you fix it, please. I called them and they sent me an email saying it's already fixed, but it's not fixed. I called them, I emailed them. So hopefully tomorrow they will fix it. Yeah. The same issue happened with me on Monday. I had a class and was hard for me to teach because even it's a DCC and mostly it's just slides, it's hard to write or do anything, it was really tough, even for the student. What I did, I told the student just join Zoom and I will use my laptop. So some of the students, they had their phone, laptop, some of them joined by phone, at least we've been able to manage it, but it's really tough. All right, so now if I give you a question now in the exam, I'll tell you find the G15, carry 15. Can you do that for me? This one, when you compare it to the 4-bit, you compare it to which one? C3. I'm sorry. Compare it to C3. All right. So C15, you compare it to C3. All right. Is there a question before we go deep? We did not draw the whole circuit yet, but we'll show you. We'll show you how it's gonna look like. We'll make it easier for you when you see the whole circuit. So far, we know how we found the new block B and G block, all right? And we know how we calculated the C3, C4, C3, C7, C11, and C15, all right? Okay, that's the whole circuit. And what I will do, okay, can you see that? I will zoom first. Let's zoom to the here. What is this circuit first? That's 4-bit adder, correct? Okay. Remember in the 4-bit adder, then let me do it here. So in the 4-bit adder, which the first block we used to find what? This block. Look at this one. So remember, we're trying to find B0 and G0, correct? And what's the delay here, if you remember? It's 1 delta, correct? Because it's 1 level circuit. Even XOR is 2 delta, but we'll assume now it's 1. Let's go to this color. All right. Okay. And let me. All right. So this block is trying to find the B and G. And here what we find B1 and G1, correct? And same thing for the bit number 3, trying to find B2 and G2, B3 and G3, right? So when we will find B0, B1, B2, B3, how long it's going to take from us to find those? 1 delta for all of them, correct? So they are not depending on each other. We are depending just on the input. All right. Then after that, okay, remember, that's the carry look ahead. And what's your input for the carry look ahead? just the B's and G's, correct? You will have it, all of them going here, same thing here, and here, correct? So that's your input. All right. Then we found the equation for C0, remember? We found the equation for Z0, C1, C2, and C3. We found the equation. And this equation is based on B's and G's, because that's your input and the carry -1. What is the zero? What is the carry 0? What's the circuit? G0 or yes, so C -1. And so if you look to the circuit here to find the C0, you see the C0 here? How you find it? Either it's coming from, either it generated, correct? Or it's coming from outside, and propagated through the B0, correct? And you OR them. Then that's the C0. All right. What about the C1? What's the circuit for the C1? It's gonna be 3-bit OR, correct? It's gonna be what's your circuit here? Either it's generated here, correct? All right, or it's ended with, it's coming from, it's generated here, perfect, and propagated here, perfect. What's the third condition? And here, another and it's going to be added to the OR. What's you have here? Either it's coming from here, because it propagated through 1 and propagated through 0. I'm sorry, here 0, and or it's coming from outside. All right. So that's the equation for the C1. What's the equation for C3? We have it, C2. So we have it, just we have to draw the circuit. So what you have to do when you do a design, it's not working. All right. So when you do a design, for the BG block here, you do a design for how many times? Do it only once, and you just copy that to this block. Perfect. When you do a design for, when you do a design for AND gates, you just copy that. So when you take a class called VLSI, it's a very, very nice class. It's going to show you how really you design the circuit on the board itself, right? So the main concept is copy paste. You build a small block and you try to use this block multiple times. If you want to keep drawing the circuit again, it's not going to finish. So you draw a block, for example, when we did the project, we built a block from the export and we kept it on a file. And we did one for the AND, two input AND, input AND, ORs. So we did small blocks. Then when we build the whole circuit, right, we just try to copy paste and connect. So here's the same concept. You already spent time by doing a design for the BG block. You copy paste. You have the XOR. You do the design once and you copy paste. Then the remaining, what you have to do, connect the cables together. That's the only thing you have to do. And that's why, if you remember, when we did the equation for the carry and the sum, we tried to use the XOR because we already built that for the sum. That's the purpose, to reuse the circuit, not to build everything from scratch. All right, so how much the delay we said here? Total? 3 delta up to here, correct? However, here it's 4 delta. Okay, for the sum, it's 4 delta. Now, can I use this circuit to make 16-bit adder? Yes. So what I have to do? Okay, what I have to do? I will. Oh yeah, here. So what I have to do? The whole thing. That's my What the circuit? It's 4-bit adder using the 4-bit carry ahead. I will copy this one. I will do 2, 3, then 4. I will copy, paste the 4. Then what I will do after that? I will build my what we call this one? Block carry look ahead unit. Now let's go zoom a little bit. Remember when we did the design for now? What's the new design we're looking for G block and for the P block? And what is the design for that? If we zoom in here, let me clean that. All right, what we will have here, remember, we will have the block BG unit. What's your input there? Remember what we did first. Remember we found the equation for C3, C7, C11, and C15. We wrote the equation. We have them. Perfect. So now, and in this equation, what we are using here? B's and G's, correct? Which is mean your inputs coming here. What you will have? All the B's from this. All the B's coming from the 4-bit, correct? And you will have the G's coming from all the bits, and correct? And based on this equation, we will find the G B0 or the B B0, correct? Clear? So that's what we need, you know. And let's just clean that again, because I don't want to make it too crowded here. What's our input here? I would say B's and G's. And those coming from the first block, because now I'm trying to find C3, right? So now, can you tell me what is the equation for this? The equation for the C3. What is the equation for the C3? When we will have carry 3? Generated at block 0, right? So you generate it at block 0, or what? Generated at coming from outside. That's why we will have C minus 1. So it's coming from C minus 1 and propagate through 0. Simple equation. And what we need in this equation? We need the GB0, which is coming from this block, right? And what we need? We need the B0, which is coming from this block. So we'll have the B0 and the GB0. Can we draw the circuit? It's just not, it's simple OR gate, or with, you know, the generated from first block, or it's coming from outside, propagated through the level 1. So can you tell me what's the difference? Don't look at the names, the input names. Can you tell me what is the difference between this circuit and this circuit? It's the same circuit. The only difference is the connection, from where your connection is coming. All right. So that's why the purpose here, you know, to find a circuit you can reuse multiple times. That's why we said, okay, let's do 4-bit adder, then we'll do the 16-bit adder, because I can use the 4-bit adder. All right. Okay. So do you have any more questions? Do you need me to go more details? I think it's clear now. All right. Now the question for you, let's discuss the delay, because that's tricky, it's a little bit tricky. All right. All right. When we will have the C3 here? 3 delta, correct? All of us, we agree, correct? All right. And what you need here, how much this one will take from you? Yeah, what's the equation here? I'm sorry. Let's go back. What's the equation for P and G? Okay, what's the equation here? You will have or 2 delta, 2 levels. So this one is 2 delta. So if we go back again, so how much here you need? 2 delta, correct? Then how much this one will take from you? 2 delta, right? Now, to receive the output, how much? So we say 3, correct? Then you will have 2, that's 5. Then you will have another 2, 7. Which one? Correct. I agree with you. So that's why I told you it's a tricky. What is our input here? Remember? What's our input? The B and G's. So it's coming from here. So that's mean I don't have to worry about this one. So I need 2 delta here. Then I need 2 delta here. Then I need 2 delta here. Still I have 6. Oh, I'm sorry. It's 1 delta. Let's repeat that. Now to find C3 here, how long is it going to take from me? I have to find the B0 and G0 and all of them, right? Those it will be my input here. Okay, so I'm not going to go through this circuit. So it's going to be connected somehow. It's going to be connected directly. Correct? It's just wire. And how this one, how much we said this one is 2 delta. And for carry look ahead is another 2 delta. So here to get this one, it's going to be 5 delta. Perfect. And it's going to take another 5 delta. Same thing for C7 and then C11. Correct? That's the trick here. So now, then it's going to take another 5 to have the C15, correct? Perfect. But the problem, what's the problem? At the last stage, you need the carry 11 because here you have a small one. Remember, you have C-1 here, and this one is coming from where? It's coming from C11. So, and how much this one takes from you? 3 delta, correct? So 5 plus 3, then you will have 8 delta. Then you will have another one for the sum, it's 9 delta, correct? So the answer will be 9 delta. I don't know, yeah. Clear? Which one? Okay, so talk about this one. Yeah, but by the end, it's coming from here or from here. But the point is not about the 15 itself. The point here, remember, this block, you need the C-1. And this one is coming from where? The block before. So that's why you have to connect it here to be able to do this one. And that's why you will have another 3 delta. Then you will have 8 delta to have the carry. But then you will add another one for the sum. Clear? Is there a question about the circuit? Again, to draw the circuit during the class, really it's going to take a long time. So This way, it's just easier, to show you the full picture, try to explain, the most important points, I'm trying to save you time, but now let's go continue. So what is the total delay? 9. Okay, that's 8 without the sum. Okay, let's continue. Now, if we use the carry, the rubber carry head, how much the total will be? Remember, for the 16, I'm sorry. Okay, now let's make it even more harder. So now how much we did up to? First phase we did 4-bit, and using the 4-bit we did the 16. Now can we expand that to 64-bit? Yes. All right. How we can do that? Okay, so the first you have 16 bits, you add them next to each other, and just what you have to do, use the carry. So when you have 16 bits, what's the last carry? It's going to be C15, C31, and C47, and finally C63. What is the delay here? We said to find the carry. To find, it's 8. 8, then 16, then 24, then it's 8 or 7. No, that's 8. Guys, you confuse me. It's 7 delta. You know why? Why we said it's 3 delta here? It's not 3 delta. This one is 2 delta. The carry look ahead takes 2 delta. So, correct? So this one, to get the C17, you need 7 delta. And to get the sum, it's 8 delta. Yeah, I don't know why. So it's 2 delta here. So that's why if you go back here, you need 7, then 14, 21, 28, then you will have 1 delta for the sum. So the total is 29. That's for 64 bits. All right. Can we reduce that? Yes. By, again, the same concept. Canceling these lines somehow. And how we can do that? Simply we add, what we will name it, this one? Super block carry lock head. And how that's going to look like? What's the time? Do you need a break, guys, or what? We still have 5? Wow, took a long time. Wow. Because all right, let's think about it. I'm not going to go deep here because that should be easy for you now. What we will do, we're trying to break these 3 lines, correct? And what we will have, hello, may I help you? Have a class? How come? That's my regular class. You missed, yeah, last week we missed it, but this week I'm here. What time your class starts? Oh, is the class registered under your name? Okay, so guys, don't move. We try to stay, but because we have an issue with the projector there. Usually my class in the other room, but we have an issue with the projector. The same issue you had last week. Okay, and you moved here, correct? Yes. Okay, see, we have the same issue. Okay. Only my Wednesday class is here. Yeah. All right, so guys, let's move the other room. So no problem. Can you give me 5 minutes? Because I will finish this one, then I will finish the class. Still, I have a lot to explain, but I cannot do it without projector. Me too. Yeah, but let me just finish this topic because I want to explain the assignment. Now let's talk about the super plot, okay? And that's going to be part of your assignment, all right? So what we have here, what this block? That's the 16-bit block. And this one we divided to 4 of them, correct? Remember, we have 4. All right. And this 4, what you will have, that's 4 bits. You will have a small CLA, correct? You have CLA, you will have CLA, you will have CLA, then you will have, okay, block CLA, correct? That's the 16. Am I in the right location? Yes. All right. So that's total of 16 bits here. Then you will need 4 of them. So you need 4 of the super block. And how we put them together? How we put them together? Using this super block CLA. What's your input here? Remember, it's going to be G super block 0, B super block 0. And the same thing here. You will have 2 inputs. You will have G super block 1, B super block 0. I'm sorry, 1. Now the question for you, can you find the carry? So what's the carry? We'll have C15, C31, C47, C63. Now if I tell you find for me this carry 15, what's the carry 15 will be? It's the same equation. If you look here, so either you remember now let's find the B. Either you you propagate it from B block 0 to the B block 1 to B block 2 to the B block 3. That's why you see B block 3, B block 2, B block 1, B block 0. What is the G? Either you generate it here, the last one, so you generate it at the G block 3, or you generate it at the B block 2, then you propagate it to block 3, or you generate it at the block number 1, then you propagate it to the other 2, or you generate it in a block 0 and you propagate it to the remaining stage. It's the same circuit. Now the question for you, is the circuit, come in, did not work with me. I don't know if somebody came and fixed it. Yeah. You want to do your class there, or you need me to move there? It's up to you. Okay, perfect. Then okay, excellent. I will send it to you. Or they can join me, that's fine. Thank you. All right, so I see everybody ready to leave now. We can stay. All right. Yeah, because I have to go over the converter. You want to leave, guys? So yeah, let me just finish. Clear what is the super block now? Now, if I ask you to make this one, if you go further, if I ask you to make 64, what's 265 circuit? Okay, so I don't know what you want to name it. You know, extra super block. Okay, so but we don't need it, you know, because our current processor is up to 64-bit, correct? That's 64-bit either. So that's why in this class we're trying to show you the actual what we have. I'm not trying to give you something really easy and simple. So that's the concept when you start from the 4-bit, then you expand it to 16, then 32, then 64. You know, it's more complicated, and that's how you speed up the computer. That's why now you have a fast computer by doing that. So now, can you do the delta analysis here by yourself? Of course. You know, you have to find the delta. So what is the assignment? And I will send it to you. But the assignment, finish the design of the 64-bit, look ahead, where look ahead limited to 4 bits. All right. So simply is that the circuit? It's the same circuit, right? So what you will do, you will draw the circuit, you will finish the design, you will find the super block G's, the super block B's, then you will find the carry, what we have, carry 15, carry 31, and carry 47, and carry 63. You will find them for me. You will do the delay analysis, correct? See how much the delay for the whole circuit. And you just try to draw some of the circuit. You don't have to go deep. You don't have to draw everything, just you have to draw simple, like, for example, what we need here. Yes, what we will name it? Super block B and G unit, correct? So that's something else. Before what we name it before? Yes, we name it block. Wait, all the way down. Why? Yeah, we name it block BG. Now the new one is going to be super block BG, right? Then maybe, ultra or something. So that's the second assignment. You want to take a break very quick, guys? 5 minutes before we go to. I want to start with the comparator because it's really a nice topic. Yes. Yeah, of course. I'm not going to ask you to do that. It's going to be a project for you. Yeah. Listen, if you have really a computer like this and you zoom in and you draw, then you zoom out, that's where we get. But no, you don't have to. And by the way, I will send you the assignment one solution so that you know your I think it's simple, but I will show you the right the exact answer. And again, there is multiple answer. You can use different way, because if you expand the circuit, or even when you do the what they call it, the K-map, if you change the sequence, it's going to give you a different equation. So guys, we need a break for 5 minutes, or we need me to continue? Continue, because you guys are leave early. Or you need me to finish with the minutes? Yeah, you can. Then you have to finish the comparator by yourself. All right. So now let's think about another design. I'm trying to compare two numbers and find if these two numbers equal, or A less than B, or B less than A. So if you have two numbers, A and B, okay, and it's 4 bits, so how many input you will have? 4 each. And what is the output? Either the A it's bigger than B, or A equal B and A less than B, correct? Let me give you some numbers and give me the answer. So if I give you 1 0 1 0 1 0 1 0, what's the answer will be? Equals, correct? Which will be 0 1 0, correct? It's going to be 0 1 0, because this 1 that's meaning they are equal. Perfect. Now if I do 1 0 1 0, then 1 0 0 1, what's the answer will be? Can you give me the answer here? That's A and that's B. It's going to be 1 0 0, all right? Because that's mean that's 1 and both the zeros. All right. Can the answer be 1 1 1? Can the answer will be 0 0 0? No. So you have don't care stages. That's impossible to happen. Correct. Now the other question for you: do we really need 3 selection here? Can we eliminate some of the output here? Can we eliminate some of the output? We can eliminate. Okay, what we can eliminate? I can do what I can do. Okay, just remove this one. All right, then we'll have A equal B or A less than B. So if the output is 1 0, what that mean? Equal. What about 0 1? Okay, what about 0 0? A bigger than B, correct? So really you don't need 3, you need 2. So what's our circuit? What's the number of input and number of output? Is 8 and output is, can we use what they call it, K-map? No, because you have 8 inputs, so that's going to be a challenge. So we have to use the slice approach, correct? But now let's think about even the slice approach. before we go deep, let's think about the logic. Now, I need you to tell me, if I have a number like this, okay. Now, can I tell which one, if these two numbers equal or less or bigger from this stage, from here? Can you tell me that from this from the first stage, can I tell if, no, correct? Still, I have to look to the other bit. Now, but if I look to this two bits here, can I tell which number is bigger? You know, that's mean if you think about it, if I look to the circuit from most significant bit to the lowest significant bit, if I look from left to right, maybe I will find the answer quicker, because I know if at the stage number 4, for example, or 3, A is bigger, that means I don't care about what's behind that, because A is already bigger. All right. If I look from the least significant bit, it's still, I have to check all of them. All right. So today, what we'll do from left to right. The assignment's going to be from right to left for you guys. So it's going to be maybe more challenge. All right. So now the question, the same thing, you know, what's the trick here? What we're trying to do, we're trying, similar at the adder, we're trying to find the B and G's, correct? When we generate the carry and when we propagate the carry. Same thing for here. We have to find another logic to tell us it's this one, you know, bigger or smaller or equal. So now the same idea. All right. So what's our circuit's going to look like now? As we said, it's going to be simply, you will have A, you will have B, and you will have A equal B or A less than B, correct? Perfect. So that's initially, that's the one bit approach. Okay, so we explained that to you guys already. Okay. All right, and we said, you know, we start from the most significant bit and go right. Okay, we start from the most, then you go to the least. Okay, and why this one? Oh, okay. So that's what we said here, correct? That's gonna be our circuit. It's gonna be A, B, and A equal B and A minus B. All right. That's for 4-bit. Now, when we start finding the equation, we try to look at stages and try to find an equation. And now you see I'm speeding up because now we know the concept now. Like, we're trying to mimic what we did in the carry ahead, but of course we tweak it. All right. Now here. So how the circuit's gonna look like, as we said before, if you're trying to find method. So this time I'm trying to find this at this stage. I'm trying to find which one bigger, A or B or equal. All right. So I don't care about anything before and anything after. All right. Now, however, what is going to impact my decision? You know, the input is coming from here, correct? What's coming from left to the right of the most significant bit to my stage? You know, this one is going to impact my decision. You know, if I already, the input's coming as A bigger than B, so what I know at this stage, still A is going to be bigger than B. And this one is going to be the same thing. It's A bigger than B because I already know it's at the most significant, it's already bigger. If it's equal, no, that's mean I have to decide if this one coming one, let's make it more clear. Now I will do 1, 0, and doesn't matter how many bits. Now let's say, you know, this one, and you remember what's my input, what's my output? It's A less than B or A equal B. So if this one coming from here, it's 1 and this 0. What I know from that? A already smaller because I'm A minus B, correct? So that's mean my A and B, it's already smaller. However, if this one come as 0, 0, I'm sorry, 0, 1, what that mean? So this one, this stage is not going to help me to decide if it's bigger or smaller, correct? Now I have to rely on this stage because this is equal. This equal, that means this one equal. Because when you have the signal, when I say it's equal and this one is coming here, it's going to affect your decision. I will show you when we do the examples, we'll make it more clear. But the point here, at this stage, okay, this two, the input, it's will have an impact, and the signal coming from the most significant bit has an impact. If it's coming as A bigger than A, that means in my stage, my current stage, I don't have to do anything. It's already A bigger than A, or A bigger than A bigger than B. Perfect. But if both equal in the previous stage and it's coming to my stage, now my stage, it will decide it's bigger or equal or smaller. If it's equal, what that's going to happen? Then next stage will decide because they're now still equal. But if in my stage say, oh, A is bigger than B, what that's mean? The following stage, still A will be bigger than B. Okay, I don't care what's the result there, what's the numbers there, because I already decided from the most significant bit that's A bigger than B. But if it's still A, if it's still equal, so if the stage number 4 equal, then stage number 3 is equal, then in my stage, I have to now check, oh, if it's equal, that's mean, okay, now the stage 1 will decide. If it's A bigger than B, okay, now we know A is going to be bigger for all the stages. So when we see that, when we see the design, you will make it more clear for you. So what you need A and B. And the signal, it's going to be A minus B. And if you see here, what we say A minus B of I plus 1. Why? Because at this stage, it's called I. So my stage, so if at this stage, it's going to be A of I and B of I, correct? And this stage, it's going to be A of I plus 1 and B of I plus 1. In the carry look ahead, or on the carry adder, because we started from the left, so we did minus 1. Here we did plus 1, right? All right, let's do the K-map. So again, that's our circuit, correct? That's the circuit. Perfect. Now, how we do the K-map? First of all, how many output you will have? 2 output, correct? How many tables I need? 2 tables. What's the size of each table? 16. Now, let's just go deep a little bit here. And so what's my input? A, I, and B of I, correct? And what is coming from the previous stage, from the most significant bit? We'll have A less than B of I plus 1. And you will have B equal B with A plus 1, correct? Now, let's put some number together, okay? So if we look at this one here, what's A or what's B? You have A and B, correct? What's A? 0? A1. Okay, what this B? 0, correct? All right. And if your signal coming from here, if the signal coming A minus B plus 1 is 0 and 0, what that's mean for you? If this one, I'm sorry, if A minus B equals 0, A equal B equals 0 for I plus 1, for the I plus 1. What that's mean for you? A greater than B, correct? A greater than B. A greater than B. And what's this equation will be? What's the result will be? Remember, our output is either A minus A smaller than B. 0, 0. Correct. So what I will have here? Have 0, and you'll have 0. Perfect. Now let's make the easy one. Let's go to this one, to this row. What is your input here? 1, 1. What that mean? A less than B equal 1, and in the same time, A equal B equal 1. Is that possible? That's not possible. You cannot have A less than B, and the same time A is equal B. What that mean? That's impossible. That's why what we write, don't care. I don't care about, and I do that for the whole line, because that's the whole line is going to be the same issue, because it doesn't make sense. You will have A minus A less than B, and in the same time A equal B. So we solve this, we finished the whole row here, correct? One time. We finished that. Now let's take this one. Now, this one will make it easier for you. All right. So what is the numbers? Both numbers? Both equal, correct? Both equal. So can I decide in this current state? I cannot decide. So what I have to log to the previous state. Now, if you look at the previous stage, what's your output? It's 1, 0. What's mean out 1, 0? It's A less than B, correct? Equal 1, and A equals 0 equal 0, correct? So what's your output? If my current stage equal, so it's gonna carry with you, because that's mean I have to decide on the most significant bit. So that's mean I will have 1, because this one is gonna A less than B, and this one the equal one, which is not equal. We know it's bigger, because now from here we know it's A bigger, smaller than B. Now, can you do that for the whole line? Yes, because always our result here, okay, remember, if it's bigger from the first stage, you don't care about the remaining. So that's why when you have 1, 0, we know it's A less than B, and that's why everything is going to be 1 here, and everything here it will be 0, correct? Clear? Now let's go up here. Now let's start with the first line. What is the first line? I have 0, 0. What means 0, 0? A bigger than? What's the equation will be? 0, 0 always. So this line, you see this line? Always going to be 0, 0, 0. All right? Because always the input here is 0, 0, which is A less than, it's bigger than B. So that means it's not less than B and it's not equal B. Because remember, our output either less or equal. So if it's not less and it's not equal, what does that mean? It's bigger. That's why I will make it zeros. 0 here, 0 here. That means it's bigger. When it's 0 here, 0 here, that means it's still bigger. When it's 0, 0, it's bigger. All right? So now let's go to the middle one, which is more tricky. Okay, let's go to the middle one. Let's go to this one. Okay. When your input 0, 0, that means it's both equal, correct? Okay. And what you have here? You have 0, 1, which equal. When you have 0, that means A less than B is not correct. When you have A equal B equal 1, that means it's equal 1. Which one has to be 1? This or this? It's going to be this one 0, and this one will be 1. That's why you will see 0 here, will be 1 here. All right? So if you do this one, what we have? You can tell here. So you can tell here what you have here. B bigger, correct? But if you look here, it's equal. So what that's mean, I have to rely on this stage, which is mean A, it's smaller than B. So that's why it's 1 here and it's 0 here. Correct? So if you think about it, it's really simple. Just, you have to be careful about that. So after you finishing the whole table, okay, what's the next step is? Combine them first, put the ones in one equation. Okay. So, and from the K-map, when you have a don't care, still you can combine them. You can combine them with ones to make it bigger. So that's why we have it here. And you will have 1 here, and that's you can combine it with this don't care, correct? Is there anything else? That's it. What about here? You have only this one, and you combine it with the don't care, and you don't go, so you'll have 2 here. Can we write the equation for that? Yeah, let's do the first one. Okay, I will try to not to show you that. Okay, so we can to think together about it. If I delete that. All right, what is the equation for, what's the one? A, I'm looking for A less than B of I, correct? That's what I'm looking for. That's my first output. And how you do that? Can you do this one for me? What this one? When you do the whole thing together. So you eliminate the top. So then you will take this one. You will take this 2. We have 1 and 1, 0. What that's mean? What's the common here? The 1. What's the 1? Is A less than B of I, correct? Or with what? With this 2, correct? What is the common here? So we need both of them. Okay. What's the both of them? It's going to be I bar B I, correct? And when you take this side, what is the common? Is this one. Okay. A equal B. AI BI of I, correct? I'm sorry, I plus 1. Yes, I plus 1. Is that the right equation? Let's just see, just to confirm. So it's A less than B at the A plus, I'm sorry. Okay. Plus 1, right? And then you will have A equal B or A bar B bar, A bar and B bar. Can you explain that to me, guys? By logic. When A will be less than B? Again, think about it. So either A is less than B in the previous state, correct? Because if it's less than the previous stage, you now anything after that, you already decide. From the previous stage, it's A less than B. So I don't care about the other. Or, what's the or? If the previous stage is equal, then I'm looking for the current. So the current, I'm looking for less. When it's less? When it's A less than B. When A is 0 and B is equal 1. That's why we did A bar and B. So you will have only 2 conditions. When A will be less than B, only in 2 conditions. Either it's already less at the most significant bit, or currently it both equal, A and B equal, or I'm sorry, it's equal in the previous stage, and A less than B in this stage. So in my stage now, I know the most significant, it's equal. So now I have to rely on my current stage, because the previous stage I could not decide because it's still the equal. Now in my current stage, I have to decide. And how I will decide if it's A less than B? Only in one condition. If it's A 0 and B equal 1. That's the condition. All right. So that's for less. Now let's do the equal. Equal, it's going to be long because we'll show you now. It's going to be because you have to, when you think about it, it's the same logic. But let's write it down. Okay, so what's the equation for this one? Now I'm looking for A equal B, AI equal BI, which level of I, correct? Equal. Let's start with this one. What this one is 0, 0. What that mean? It's AI, BI, both bar, correct? All right. And this side, where is the common? Is 1, 1. What is 1, 1? Is the equal, correct? So which is A equal B at the I plus 1. All right. So that's the first one. Or, what's the or? Can you tell me? Here, let's look here. What we have here? A, B, correct? And it's the same thing. A equal B, AI1. All right. Can you explain that to me? It's pretty simple. Think about it. When the numbers are equal at this stage, it's my stage. When that will be equal. First one is when my previous stage, it's already equal, and my current stage still equal. And equal, how many equal condition will have? Either 0, 0 or 1, 1. That's why it's already equal in the previous stage, and then this one 0, 0 or 1, 1. So when you really think about the logic, it's really easy. You know, just you have to think about it. When A will be equal B for any stage. So what the first step I have to look? The previous stage. If the previous stage is already equal, now is my current stage equal? If it's equal, that means still the two numbers equal. Okay, I'm talking just this stage. Now, when I move to the next stage, so I check it again. Is my previous equal? Or it's equal? Okay, now what's my current? If it's my current equal, that means still equal. Then until I reach out to the last step. When the other question, when A it's less than B. When? You have two conditions, correct? Either at the most significant bit already A less than B, or what? Or the previous equal and my current less, right? A less than B. Clear? So that's the equation. So what we have two equations. We have this one, and we'll have this one. And again, you know, because that's a common, so you combine them together. Correct? What's the time? Yeah, let's try to just to speed up the process. Now let's talk about the delay. All right, so how the circuit is gonna look like? Remember, that's 1 bit, correct? You will have A3 and B3, correct? And what you will have here, that's from outside. Usually, when you do the first bit, what's the input from outside? What you will assume? Equal. So always it's gonna be 0 and 1 at the beginning, correct? All right, then you will do the equation. You will have two equations, and you will have your output A minus B or A equal B. I'm sorry, A less than B or A equal B, correct? Then this two, the output, it's gonna go to the second block, because that's gonna help us to decide, okay, if they are equal or less or more than that. So what's the second block? It will be A2, B2. Then it's gonna go until you reach out to A0. Then finally, the final result is your result. That's the final result. Now, the question for you, what is the delay? What's the delay here? So let's this one, you bring it down to 3 delta, correct? Or 2 delta, 2 delta, let's say. All right? Or let's say, okay, 3, let's say, it's a 3 delta, correct? Because, remember how many stages you have. When you do the equation here, I'm sorry, what is the equation here? It's a 3 level, because you will have and you will have the inverter. So If you count, if you do the path, you will have 1, 2, 3. So that's a 3 delta. So this block is going to take 3 delta. And to get the final result, how much you need? You need 3, 3, 3, and 3, 12. So the final will be, it's going to take 12 delta to have the result, correct? So the total will be 12 delta. Do you have any question how we found the delta? So each block is going to take 3 delta from you, and you have 4. So it's going to take 12, total of 12. Now, again, how we can speed up the process again. What we did with the carry issue, we tried to, yes, we use the, look ahead, but what we did, we try to break the connection. We try to find if there is a way to find A less than B and A equal B before, that's going to help us to speed the process. All right, so that's how the circuit is going to look like. And we will see how we can build the look ahead unit. All right, what we have here is pretty simple. That's your input. A and B is A and B and A and B, and you will have signal from here. It's going to tell you. So now, question for you: when is this one? When is this one? Will be A equal B? Can you tell me when in this stage A equal B? Yes. So correct. So that means first here has to be coming as equal. Yeah. What's the second condition? And so, and this current, this two equal, and the previous is equal, correct? And how you will decide if this one A less than B, how you will decide that? First condition, if here already A is less than B, that means it's gonna aggregate all the way down. That means everything is gonna be A less than B, or equal here and A less than B. That's really the condition. Even if you want to go here, can you find when this one is going to be A0 B0 equal? When equal and currently equal, then the result will be equal. Now what about if here, how are we going to make sure this one A less than B? Okay, either it's here less than B, or equal here but less than B here, or it's equal here less than B, or finally it's equal, then here it's A less than B. All right. So when you understand the logic, everything else will be easier. All right. So to break these lines, we need a look ahead unit, correct? What's your input going to be here to help you to decide? Okay. So the trick here, remember in the carry look ahead, what we did, we entered the B and G. We tried to find where we can generate the carry and when the carry is propagate to the next stage. So at that design, we did B and G. So here the similar thing. We have to find something similar to the B and G's, but for the comparative. Okay. So that's the two signal we are looking for. And what's which one? All of them are less equal. Okay. Okay, that's what you do for bit. For example, you can solve it in case you can solve it with 4-bit comparator. When you have 16-bit comparator, can you use the OR gate? Yeah. You get yourself. Again, but that's you're adding the delay. Yes, you can use the OR gate or and keep just ORing, then you will have delay forever. So adding more gates, you're adding more levels, then of course you'll get to the point you cannot have the right answer. All right. So from previous, what we said about A minus B, how we found that? We say either it's less than B in the previous stage, or it's equal in this current stage, and A of I is bar, like, it's 0, and the B is 1. So that's the only, you have A, it's less than B. The second condition for A equal B, when we have that, if it's equal at the previous stage, and the current stage, either 0, 1, or 1, 0. I'm sorry, either both zeros or both ones. That's why we have it like this, right? So guys, do you need me to stop or continue? It's too much for you today? Too much? All right, so let's stop today. So we'll continue next week. Make sure you work on your second assignment. I will post it in the Canvas so you can grab it there. If you want to submit that through, just write it, type it, give it to me, or you want to email it to me. Yeah, just email it to me. That's fine. But try to use, which email, guys, you usually send me? Which, my student email or my faculty email? Yeah, just use Muhannad at Bridgeport. Don't use Muhannad at my Bridgeport. Just want to go and look on one location. Yeah, because both is still active. I don't know why, but that's fine. All right, so I will send you the assignment. I will send you the today note, and we'll see you next week. Thank you, guys. Is there any question? It's complicated. I know it's a lot of information. Actually, it's not a lot of information. It's a lot of steps, but it's the same concept. All right. I'm sure if you go review it again, you will understand the trick how to find the BNGs, then how to find the super block. And after that will be really simple. Even if I give you any circuit, you build the 4-bit block, then based on that, you start building, make it bigger, bigger, bigger. From 4, 16, 64 to, that's enough. If you want to do 265, that's fine, but there's no need. Did I, okay, stop.